Alrighty, so today we're going to be looking at nuclear half-life, and this will be a pretty short video, so don't have to get too comfy. Alright, so first off, what nuclear half-life is. So the vast majority of substances break down at some sort of rate, and those that break down at a more quick rate are going to be considered the radioactive substances. And so these substances, they have a huge number of nuclei on them, so a various combination of protons and neutrons depending on what their isotopes are. But those nuclei, they don't just all of a sudden break apart. It takes time, and they'll slowly go through their own little process. But that process is completely random. It's basically a statistical chance will this happen. It's not going to say this will happen this many times every this often. It's saying there's a this percentage chance that this particular exact atom is going to undergo this certain decay. And so whenever you have a whole group of or a large quantity of data points or something like that, and you have something random, you can still statistically pretty accurately predict what's going to happen. And so that's what a lot of this half-life depends on, is even though it's a very random process, it is at the same time predictable because it's all based on chances. And again, whenever you have more chances for something to happen, you can be more accurate with your predictions with it. So the number of decays that happen during a specific time period, that's going to be proportional to the number of nuclei in a sample, meaning that if I have more nuclei, so let's say I have 10 atoms versus 100 atoms of a substance. If I have 100 atoms, I'm going to have probably 10 times more decay happening because there's 10 times more things. Again, this nuclear half-life stuff, it doesn't depend on how many atoms there are. It simply matters on the atoms themselves. So it doesn't matter whether you have 5 atoms, 100 atoms, 15,000 atoms, 500 million, billion, gajillion. Every atom is just as likely to decay at any given point. It's just that whenever you have more of them are likely to break down. So mathematically, this is going to be an exponential function. So the graph is going to curve downward. And the nuclear half-life is defined as how long it takes for half the nuclei of a specific isotope to decay. So basically, if I start with 1 million atoms, how long does it take for those 1 million atoms of this particular isotope to break, if I have 1 million atoms, half-life is how long does it take for 500,000 of those, so 500,000. How long does it take for that 500,000 to break down into whatever the daughter isotope is going to be? And we denote that with T1 half. So it's anywhere you see T1 half, that's simply going to be referred to as the half-life. And so the isotopes of each element are going to have different half-lives, and they can range from microseconds for the really, really unstable ones, the ones that we create in nuclear colliders and nuclear reactors that are basically just exist so that we can point it and say, oh, look, that's a thing that exists, and then it goes away. Or it can be longer, it could be seconds, days, hours, or it could even be things that are so incredibly stable that they just virtually don't decay at all. And so it's a whole big spectrum as to what happens with that. So again, half-life is amount of time it takes for half of the original amount to decay. So if I start out with 200 grams of an isotope, half-life is 2 years on it, and I want to know how much is left after 6 years. So I know that if the half-life is 2 years, I have a total of 6 years. I'm going to go through a total of 3 half-lives. So after the first half-life, we're going to be down to 100 because divide by 2. Divide by 2 again, we're at 50. Then after the third half-life, we're going to be at 25. And it's as simple as that. Now you could get more complicated things like that, but the majority of what we're going to be looking at, it's going to be simple, pretty simple, easy calculations like that, where you can basically just use your fingers and some quick mental math, and you're going to be good to go. If you want an actual math way of doing it, so whether you don't want to use your fingers, or if it's something more complicated, like maybe you have 2.67 half-lives happening, you can't exactly count that with your fingers, and most of us can't do that in our heads. So we've got this nifty little equation here. So in this, y equals x over 2n, y is going to be basically what we wind up with. So after all of the half-lives have occurred, after all the decay process, this is how much of the original sample is going to be left. X is how much did we start with, and then N is going to be the number of half-lives that get or that happen. Now, just note this is the number of half-lives. This is not the actual half-life. So if something has a half-life of 2 years, do not plug 2 years in for the top. You have to plug in the number of them. So for the previous problem, we would put a 3 in for N because there were 3 half-lives that occurred. So 200 over 2 to the third is going to give us 25. All right, so half-life of an isotope, 5 seconds. So we want to know the mass of the isotope 30 seconds from a starting sample of 8 grams. So as we're going through this, first thing we need to do is figure out how many half-lives we have. So if one half-life is 5 seconds, it's going on for a total of 30. So 30 divided by 5 is going to be 6. So we have a total of 6 half-lives. Or you can also count out 5, 10, 15, 20, 25, 30. So you get up and you know that we have 6 half-lives happening there. So if we started initially with 8 grams, I know it's going to decay in half 6 times. So it's going to go down to 4, 2, 1, 0.5, 0.25, and then 0.125. Or if we round, we'll get down to 0.13. And again, you could plug in your values there. 8 for our initial starting value. And then we'll plug in 6 for the end because, again, we found that there were a total of 6 half-lives that occurred. And we're good to go from there. All right, and last example. Half-life of an isotope is 3 hours. How long in hours will it take for a 500-gram sample to be reduced to 62.5 grams? So again, we simply need to figure out how many half-lives have occurred. So you can either count up, so multiply 62.5 by 2 until you get to 500, or start at 500 and divide by 2 until you get down to 62.5. Since I don't feel like multiplying a decimal, we're going to go down. So 500 to 250 is 1, then to 125, and then to 62.5. So I know that there's a total of 3 half-lives that occurred. So then we, if total of 3 half-lives happened, 1 half-life is 3 hours. 3 times 3 is going to give us 9 hours. You could also plug this into that equation, but you got to know how to use logarithms and all that stuff, and I quite frankly don't feel like dealing with that. And I will not blame you if you don't want to either. So, that's all there where we really need to do for half-life.